Hi everyone, welcome to the Developer Student Clubs at UC Santa Cruz. Today's workshop is an introductory level workshop on TensorFlow. The goal is to build a good foundation on TensorFlow and run through a guided tutorial which provides students with hands-on coding experience. Once you have finished this introductory code lab, you can move on to more complex TensorFlow code labs to further your journey in learning about TensorFlow. Alright, let's get started. Here are the topics that we will be covering throughout this workshop. We will first look into what machine learning is, how it's used, and how it's veiled in various forms of technology that you may use on a daily basis. We will then cover neural networks and how they're used in machine learning. Next, we'll go through an introduction on Google Colab, which is the service that we will be using for our workshop today. Then, we will be learning about the TensorFlow, Numpy, and Keras libraries. From there, we'll jump into coding and we'll create a neural network, train this neural network, and then view the results. Here are some tips that we have compiled to maximize your learning experience throughout this workshop. We encourage you to pause this video and rewind when necessary to fully understand the concepts that are being taught. We highly encourage you to play around with the functions and the code after learning them to solidify your understanding of them. Next, make sure to pause the video before our teaching team moves on to succeeding coding segments in order to see if you can derive the solution on your own. And feel free to pause this video and search up any concepts to get a better understanding of them. Go at a pace that you're comfortable with and make sure to get a good grasp on a particular concept before moving on.
Now let's talk about what machine learning really is. So what you guys have been doing so far is what's called traditional programming. Traditional programming involves giving a program a set of inputs, a set of rules to follow, and then the program will determine what outputs correspond to what inputs. Machine learning is sort of the opposite, where you give a program a set of inputs and also the corresponding outputs. Now, the program will determine what rules to follow in order to get from a corresponding input to its output. Now let's talk about some real-life examples of where you might use machine learning as opposed to traditional programming. The first main example is in image recognition. Now let's say you're trying to make a program to determine whether or not a given image is one of a cat or one of a dog. Now, from your perspective, what makes a dog a dog? You may think that the way that the face is shaped, the way that the body's shaped, that's what makes a dog a dog. But how would you program that? It's very difficult to tell a computer that, okay, I want you to look at the facial structure and the body structure, and then you can say it's a dog. Now, this is where machine learning comes in handy, because you can train the computer to look at different patterns and say, okay, because I've seen this, and this pattern, this image is one of a dog. This is a very useful tool because the computer can make out patterns that you might not even come up with yourself. Now, another sort of use for machine learning is for synthesizing text from voice. This is useful in devices such as the Amazon Alexa or the Google Home. When you tell Google Home to do something, then Google takes your voice and turns it into some block of text. It then uses natural language processing to figure out what exactly you were trying to say, and it completes your request. So that's a little bit about machine learning and how it differs from what you guys.
In this code lab, you will be working with something called neural networks. Neural networks are a set of algorithms modeled loosely after the human brain that are designed to recognize patterns. A neural network is a model that takes in a set of inputs and outputs predictions for that input set. For example, you could have a data set of speeds x that you feed into your neural network to return modes of transportation, such as a bike, car, or airplane. This would be your y dataset. Each layer of your neural network consists of a quote-unquote neuron that takes in inputs and activates them based on a linear combination of the inputs and weights. To break this down, each neuron is a mathematical operation that takes its input, multiplies it by its weight, and then passes the sum through the activation function to the other neurons. Weights transform the input data within the network's hidden layers, seen in the image on the right. They determine how important each of those inputs are in making a final decision and if they are increasing or decreasing the probability of your thesis. So, what is it used for? Neural networks are used in so many ways, such as speech recognition, anomaly detection, computer vision, the list goes on. Essentially, you refine your neural network for whatever problem you're working with to make the best predictions possible for your dataset. In this particular code lab, you will be building a neural network, training it to find a relationship between the X and Y datasets, and using it by feeding in your own values to get a predicted outcome.
I'm going to be briefly introducing you to Numpy and some of its features. Numpy, which is an acronym for Numeric Python, is a library that is used within the Python programming language. It consists of multi-dimensional array objects and a collection of routines for processing those arrays. It is a fundamental package for scientific computing and enriches Python through the use of data structures, which help with efficient calculations with matrices and arrays. This package is able to perform calculations over entire arrays, which makes it a lot more efficient than Python's lists. Python uses lists which serve the purpose of arrays. However, these lists tend to be slow to process. To resolve this, Numpy provides an array object that is up to 50 times faster than using normal Python lists. This powerful n-dimensional array object is referred to as ND-array and provides several supporting functions that make working with ND arrays very simple. The reason that Numpy is so much faster is because Numpy arrays are stored within one continuous place in memory, while lists are not. This means that processes can access and manipulate them very efficiently. So arrays within Numpy are tables of elements of the same size and of the same type. If an array containing different types is created, Numpy will recognize them all as strings. So for example, if your array contains an integer, a boolean, and a string, Numpy will read them all and treat them all as strings, which makes it essential that you go back and make sure that your array contains the same type. This is also another reason that Numpy is able to be so efficient. It's because it assumes that everything's of the same type. Dimensions within Numpy are referred to as axes, and the number of axes is the rank. One way to create arrays in Numpy is by using normal Python lists or tuples, which are accessible through the array function. When creating an array, you can also explicitly define the type of array that you would like to create. To initialize Numpy arrays, we can use nested Python lists. Elements are then simply accessed through the use of square brackets, just like you would normally. Numpy also adds support for a variety of other things, including high-level mathematical functions, such as linear algebra. It also adds support for functions for features such as Fourier transformations, random number capabilities, and stacking. Numpy makes performing operations such as addition, square root, standard deviation very simple. It also has capabilities for various special functions. These special functions include things like sine, cosine, tangent, and log. Additionally, Numpy contains tools for integrating C as well as C++. One important thing to note is that Numpy will not be included in the initial installation of Python. What this means is that you're going to have to install it separately after you've already installed Python. To use Numpy, be sure to import the package prior to writing the rest of your code. And to install Numpy, if you have not done so already, you can go to your command line and type in pip3 install Numpy. And that will install Numpy and you'll be able to use it.
What is TensorFlow? It's a free and open source software library for data flow and differentiable programming across a range of tasks. It's a symbolic math library and is also used in machine learning applications such as neural networks. It was created by the Google Brain team in 2015. It's a Python-friendly, open source library for numerical computation that makes machine learning faster and easier. Twitter, Google, Visco, and Intel are just a few examples of companies that have used TensorFlow within their products. TensorFlow contains a library called Keras and is used to build neural networks. It was developed by Microsoft and was released in 2015 as well. It's a primary machine learning library that is currently used in the industry. Apple, JP Morgan Chase, and Wells Fargo are just a few examples of many companies that use Keras within their products.
Now let's talk a little bit about Google Colab and Numpy. Google Colab is a way to run Python scripts in a piece-by-piece format, and it's used widely by students, professionals, machine learning people, people in artificial intelligence, people in research. It's used everywhere. Now, because it's a very useful tool, let's start to get a little bit familiar with it because we're going to be using it in the next segment of this workshop. Now, Google Colab runs in cells. Cells can have two types. They can either be text cells or code cells. Now, this first cell over here is a text cell, but we'll talk about that later. But let's first talk about this code cell over here. In order to run a code cell, hold Shift and press Enter, and it should run the cell. Notice how all I did was I stored a string into this variable called hello world, and I printed hello world, and this was my output. Another way to create output is by simply typing the name of the variable and pressing Shift Enter. Now, the way that you can do that between this cell and this text cell over here is by hovering between the two cells, clicking code, and entering whatever you want. Now, over here, I'm just going to type in hello world, and notice how we got essentially the same thing, but with slight differences. We ended up getting these two tick marks at the beginning and the end, and that just signifies that you didn't use the print function, and Google Colab had to sort of interpret what you meant. Now, this cell over here contains Markdown. If we double click, we can see that I used Markdown in order to create this cell. If you want to create your own Markdown cells, you can either click this text button over here, or you can hover between two cells again and click the text option. Now let's look at more of how you can code using Google Colab. This cell over here defines some sort of a function. And now in order to use the function, you first have to run the cell. Now that we've defined the function, we can call it. This function is a simple function that just counts from 1 to 10. Now, notice how earlier I talked about how you need to run cells in the order that you want to use them. For example, if I run this cell first, I'll get an error saying that z is not defined. However, if I run the first cell, I'm able to do that properly because the way that Google Colab works is that instead of killing the entire program, it only kills that specific cell. Now, if I run this cell over here, you can see that I added 10 to z, and I'm able to print it out successfully. So now let's talk a little bit more about NumPy. In order to use NumPy, you first have to import it. A common way to import it is to import NumPy and to give it an alias called np. So now that we have np imported, we can start to use np's various tools. So the cell below creates a NumPy array using the function nparray. Now, the only argument to nparray is a regular Python list. One important thing to know is that everything inside the Python list should have the same type. We'll get to that later. And the second part of the first cell is just a declaration for a regular Python list. So let's run that, and let's print out both of our objects in the ways that I talked about earlier. Now, notice how the npr variable has this extra array around it. That signifies that this is a NumPy array. Now, something that's important to note is that everything inside this NumPy array has to be the same type. In fact, let's run this cell down here and see what type's associated with npr, and we can see that it's a 64-bit integer. Now, for those of you familiar with data structures in C, this is because the np array is a pointer to an actual C array where everything is the same type. For those of you who've taken C, you know that all arrays are the same type, and there's really no way to get around that. Now, here in Python, if you just use a regular list, the regular list is a reference to a variable length array of pointers. And since pointers themselves are the same type, you can store whatever you want in a Python list. Now, let's say we were to give our np array a list of different typed elements. In that case, what would happen is that our data type would be of type object, and that sort of loses the entire reason why you were using a NumPy array in the first place, as you've essentially just created a Python list. So in order to avoid any problems in the future, just make sure that everything inside your NumPy array is of the same type. So now going forward, given a few arrays of the same length, we can stack them to create a matrix. So this first line in this cell uses a list comprehension to create 5 different NumPy arrays. By different, I mean they have different references, even though they might contain the same contents. And we're storing these NumPy arrays into some sort of a list. And by list, I'm referring to a normal Python list. Now we can use the np.stack function to stack these lists, to stack these arrays on top of each other to create a NumPy matrix. So now let's run that, and let's print out np matrix, and we see that didn't work. Now, why didn't that work? The reason that didn't work is because I was passing in the wrong thing, and I should have been passing in list of arrays. And now we can see that it works. Now this over here is a demonstration of why people use Google Colab. Because when you mess up, it's very easy to just go back and make a minor change and rerun your code, and you don't have to wait a very long time for everything else to run. Now that we have our arrays and matrices, we can start to perform operations on them. The first important thing to note is that you can just add 2 NumPy arrays together. So over here, let's take list of arrays 0 and add that to list of arrays 1. If we add them, we can see that it did an element by element addition, and we got another NumPy array. Let's do the same, except let's multiply them. List of arrays, and over here we see that it did an element-wise multiplication. We can also multiply a scalar to an array, and it will do an element-wise scalar multiplication. And we can also take 2 arrays and do a dot product. So this is the same array as before. We can just do list of arrays 0, list of arrays 1, and now we are truly doing a dot product. So over here, we can now do a matrix multiplication between a matrix and a vector. So if we run this, we will see that we ended up with a vector. That's because we know that our matrix is a 5 by 5 matrix, and then our array is of length 5. And those of you familiar with linear algebra know that the number of rows the number of columns in the first argument need to be the same as the number of rows in the second argument. But you may be wondering that that list of arrays 0, that was just a horizontal array. Now NumPy does its best to interpret what you mean, and we'll see more of that in a little bit. Over here, we can now observe the shape of NP matrix, and this is important because you can reshape your arrays into any shape that you want, as long as it's a valid shape. Now over here we can see that NP matrix has a shape 5 by 5, and that's something that we were able to observe visually as well. However, let's say we don't want a 5 by 5 matrix, we want to flatten it into one vector. Now we can specify that, okay, we know that NP matrix is a 5 by 5, we can give it a tuple, or in this case, our tuple just contains one thing, but we can give it a shape. In this case, we can give it a shape 25. As you can see that it spits out an array of length 25 and you can see that you have your first row here, your second row here, and so on. Now, if you're unsure of the dimensions, which is often the case, you can just use -1 as a placeholder for one of your dimensions. So let's run this cell, and then we can see that that NumPy was able to figure out from this -1 that our array needed to be of length 25. And we can do the same thing over here, where we specified our second dimension, but we were unsure about our first dimension. We passed a -1, and we can see that NumPy was again able to figure it out. So now that you're familiar with NumPy and its various tools, you can come back to NumPy because there are a wide variety of different functions that I was unable to cover, and you'll explore NumPy a little bit further when we talk about TensorFlow and Keras.
All right, guys. So now that you know a little bit about what machine learning is and how neural networks work, we are now going to proceed to the Colab, where we're going to build our first neural network to predict linear regression.
There's two components of what we're going to be doing here. There's the Colab network notebook, which, as you saw, is sort of an interactive environment for writing and running Python code. And then there's also the Code Lab, which is sort of a walkthrough provided by Google that is sort of walking through a bit of what we're going to be doing. So let's go ahead and exit this. So you can get the Colab and make a copy of it, as well as open the walkthrough, which I have here. So we're going to go ahead and make a copy of this. And here we are in our very own Colab.
And we'll also be starting on slide 4. Create your first machine learning model. So as you can see, like the first 3 are sort of like what we've covered in the previous slides. And now we'll be starting at slide 4.
Yeah.
Okay?
So
yeah, go ahead.
What we're going to be modeling here is the relationship between these two sets of numbers. As you can see, this is actually a line with an equation of 3x plus 1. And we're going to try and see if we can train the model to predict the values without knowing what the line is beforehand.
Right, and as you can see now, we have to import the libraries that we studied beforehand. So you'll be using TensorFlow, Keras, which is a part of TensorFlow, and Numpy. So these will be very useful libraries that will contain functions to build our model and help make the predictions for the line that we're trying to predict.
So the first thing we're going to be doing is creating our model. So as we can see in this line here, we're going to create a new model with an input shape of 1.
Right, and so a little bit about this function, right? So tf.keras.sequential, that's the function that's going to create like the base of the model. But then to create each individual layer in the model, that's what we're specifying dense with. So the number of units corresponds to the number of layers in your model. Since we're just predicting like linear regression or values for linear regression, our model is relatively simple. So we just have 1 layer. And we take an input shape of 1. All this means is we will be training for data that has like 1 weight.
Yeah. So now that we've created our model, there are 2 things that we need to specify here, and that is the loss function and the optimizer function. The loss function is basically how the model is going to measure its accuracy. So basically, we want to tell how close the model is to where we want it to be. So in order to model this relationship, we need 2 values, which is the slope and the intercept of our line. And the loss function will measure how close the guessed answer is to the correct answer. The optimizer function will look at the loss function and, based on the result of the loss function, decide how it can change the model in order to minimize the loss.
Exactly. So just to recap, your optimizer is the function that you'll be using to minimize the amount of loss you're getting. And then your loss is pretty much just the function you are trying to minimize. So like for specifics, our optimizer is using stochastic gradient descent to minimize our mean squared error function. And we'll learn a little bit more about what those 2 exactly are a bit later.
So the next thing we need to do is provide our model with some data. So as you can see here, we have some sample data, which is these 2 arrays. This is going to be our X data, so the input data into the model. And this is our Y data, this is what we want it to guess for each data point. So there's these pairs of data points. So each pair of numbers here represents one data point with the input and the expected output. And using all of these, we can try to train it to predict numbers that are not in this data set.
Yeah.
So we can
So
plot
go
it
ahead
as
and
well.
run it,
Oops.
and yeah, sorry. So yeah, you can go ahead and run the previous function, and then you can run the plot.scatter function in order to get your line. So as you can see here, this is a fairly straightforward model like that you'll be designing. It's just a line, like a linear line that maps x to a particular y value.
Yeah. So now we need to train our model. So to do that, we call this function model.fit, and we provide it with the training data and the output data. And the epochs specifies the number of times that the model should optimize, the number of times the optimizer function is called.
Exactly. So think of epochs as like I think of epochs as like iterations. So each epoch does one optimization on all your weights. Second epoch does another optimization, and so on and so forth until you get to the end, where hopefully your loss has been minimized to a point where your model correctly fits the line.
So we can try running this, and we'll see that it runs about 200 times. And by the end, we have really quite a small loss function, which is going to be our mean squared error in this case.
Yeah, so again, small loss values are good because that means that the difference between your prediction versus the actual is actually quite small. So if you have a like really low loss, that means that your model is actually pretty accurate and is a good fit for the data that you're trying to predict.
We can also try making a new prediction by providing the model, now that it's trained, with a value that it hasn't seen before. So for example, if we want to predict the number 10, our model is 3x plus 1, so we know it should be about 31. As you can see, though, it did get pretty close.
Right. So if you're wondering why it's not exactly 31, that's because the model has still not really like fine-tuned the prediction for like the data set. So like it doesn't really, it's basically making a prediction in order to like predict what 10 would like most closely output to. So even though we know beforehand that this is just a line that's modeling 3x plus 1, the model does not know that, and so makes as close to an approximation as possible for that value.
We can also try plotting our predictions, but in order to do that, we need to slightly modify our training function. So let's rebuild our model very quickly by rerunning these cells. And this time, we're going to set a new variable, it can be called anything here, equal to the result of our training, and train it again. And now we can plot the history of the loss function on our model so we can see it in a nice graph. So in this case, we need to make sure that the range here matches the number of epochs that we were training for, which in this case was 200.
So make sure that's 200. And as you can see here, we get a nice plot that plots basically the loss over the epoch. So each iteration, as you can see, right, each iteration like printed out a loss if you go up in the output. And so that's basically just the scatter plot is basically just plotting each loss per epoch.
And as you can see, by epoch 25 or 50, the model is actually pretty optimized. And after that point, the training was not super useful.
Right.
So how exactly does this work? Well, we know that the relationship between our data is a line. And in order to model a line, we need two values, the slope and the intercept. So those two weights are the things that we are attempting to train and what we're trying to optimize during our training state. And in order to determine how good our model is, we use this mean squared error loss function, which basically sums up or average is the sum of the difference between the predicted value and the expected value for each data point.
Right. And how does this all work? How does this all tie in? Well, we tie everything up using gradient descent. So the algorithm over here, again, don't really need to focus on the math too much, but essentially what it's telling you is for each iteration or each epoch, you will be adjusting the weights so that it matches the actual values as close as possible. So again, the more times you run this gradient descent algorithm, the more accurate your model will get. And so that's essentially what we've done when we were creating our model up above.
Basically what we're doing here is we're taking our loss function and then we're taking the partial derivative of it with respect to each of our two theta values, which then gives us this new function. And each time we run the optimization, we're basically just updating each theta weight with this new theta weight that is the original one minus some small amount. The idea is that this will slowly bring it closer to the two theta weights that minimize our loss function.
Exactly. And now you can actually try your own data, like play around with your own data set that you create. Like, for example, you can create like a set of X and a set of Y, and you can see whether or not your model makes like accurate predictions. So over here, we're just going to do a quick example. So this range function over here just prints out a set of values from 1 through the value you specify in the function. And now in your Y data set, we are using list comprehension in order to get a list of values that correspond to each value in your X. So again, you can try this out, run this cell, and then run all the steps from above in order to get a nice model, and then you can test out your own prediction. So over here, we can do exactly that. Make sure to not run the previous data sets that were given, because you want them to map to the data sets that you created. So make sure you run those, and then now you can run model.fit, and again, as you can see, your model should minimize the loss as close as possible.
You can
And
also
thus make a
change the number
prediction
of
from
epochs to cause it to run for longer and thereby decrease the loss function even further. And this time when we predict 10, the function that we gave it was 2x plus 4, so that should go to 24. As we can see, it got 26, which isn't that good actually, but we can also see that our loss was higher here. So that could mean that if we run it for longer, perhaps we can further minimize our loss. So you can try that yourself. Try predicting different values, changing the number of epochs, and as well as trying different data sets. Yeah, we can see here that this time our prediction did not reach a point, it didn't really level off basically, so our loss was still decreasing. So if we increased the number of epochs we were running this for, then we could decrease our loss even further and get closer predictions.
awesome. Yes, so now that you guys have a little bit of intuition into how like linear regression models are created, we're going to try something new now. We're now going to create a model that will accurately predict polynomial data sets. So as you can see here, we will be taking in an input of not only just our X values, but our X squared values. Because as you know, polynomial functions are for like higher order degrees would be values of 2 or higher. So the degree for our previous one was 1, whereas for here, we are trying to create models that will predict values that are 2 or higher. In this case, we are specifically doing a degree of 2. And so polymodel equals tf.keras.sequential is the same command that you ran before, but we are changing our input shape from 1 to 2 to account for our two new like biases or 2 new coefficients to calculate. And over here, we will now be doing, we will now be compiling our model in order to get the regression model that we want. So once that's done, you should get no errors. we will now be running this data set. So as you can see here, our range is 5. So again, remember that's values 1 through 5. And then our y values are going to be corresponding to the function 2 plus x times x, or x squared plus 2.
2x squared, actually. 2 times x times x.
2 times, oh, my bad.
Anyway, yeah, so we can see here, though, the difference is when we are doing polynomial regression, we need to provide the model not only with the x data for each input, we also need to provide it with x squared and x to the n, basically up to the degree of our polynomial. That's how we can tell it what degree of polynomial we're looking for. So we're going to provide it, we're going to augment our input data, xi here, with the original array of just the numbers 1 to 5, and then also an array of the numbers 1 to 5 squared. So we can look here and see that it's actually an array of pairs of numbers instead of just a single list of the numbers 1 to 5 for our inputs.
Yes. Notice how you have your x values and your second column is your x squared values. So essentially we're feeding in our model another column of x squared values. So after running that command, we will now be training our model. So similar to before, you will be calling the function model.fit, and you will also be passing in the respective arguments. So as you can see, we have to pass in our new x and y values and specify the number of epochs. So yeah, make sure it's reasonably big. We'll do 200 for this exercise. And after this is done running, we can again see that loss is actually super low. So that means that our model is fairly accurate when it comes to predicting specific x values. So as you can see here, okay, it's a little unclear, but basically what this scatter plot is showing is over the course of the epochs, how much is the loss decreasing by? So as you can see, the loss drastically drops, meaning that the model has already pretty much made accurate predictions based on the inputs that are coming in. And eventually it levels off to a value that's close to 0, meaning that training is practically done and the model has finalized the weights that optimize your predictions, the correct predictions.
Now that we've trained our model, we can try making a prediction. So in this case, when we make our predictions, just like with our original input data, we need to provide it with x as well as x squared up to xn, where n is the degree of our polynomial. And we can see, so in this case, we're predicting 10. We're providing it with 10 squared, which is 100. And based on our function 2x squared, the output should be 200. As we can see,
So there is a small error. So we have to specify a history object over here. So we called it polymodel, but it's actually supposed to be called hist. So if we were to rerun the cells that we pretty much had before, we should be able to get rid of that error.
Yeah, so make sure to not overwrite your model. As you can see, I set polymodel equal to the result of this, which overwrote the model. Anyway, now that we've done this, we can now see that it predicted 193, which is not quite 200, but it's not too bad either.
Right. So now that hopefully we've showed you how to create models, now it's your turn to maybe create some models of your own, and pretty much experiment with neural networks. So we've pretty much concluded the Colab, and if there was anything that was confusing, please feel free to pause throughout the video and make sure to also search up commands or search up functions that were not necessarily clear when we explained it to you guys. And we hope that you guys learned something from this.
So, what can you do next? There are a couple more labs available in this series. In the Introduction to Computer Vision lab, you'll go beyond the basic hello world of TensorFlow that we covered in this workshop, and apply what you learned to create a computer vision model where you train an image classifier for fashion items. This would be a scenario where writing rules are much more difficult than what we just did, so it would be classified as a computer vision problem, where we will recognize different items of clothing trained from a dataset of different types. In Introduction to Convolutions, which is the following lab, you'll learn about convolutions and why they are so powerful in computer vision scenarios. A convolution is a filter that passes over an image, processes it, and extracts features that show a commonality in the image. In this lab, you'll see how they work by processing an image to see if you can extract features from it by scanning every pixel in the image, and then looking at its neighboring pixels. This will help you prepare for using convolutions in deep learning scenarios to make convolutional neural networks.
Please make sure to follow our social media, join our mailing list, and also please provide us with feedback as to how the workshop went. We would love to hear about what we could improve to make our remote workshop better. Thank you guys for listening, and we hope you enjoyed this workshop.
Thanks so much, everyone.